Okay, so in this lesson, I want to focus on this idea of what are known as atomic orbitals. So, as scientists went on, they started to try and develop a more sophisticated or more, let's say, accurate model or representation of how the electron hung out outside of the nucleus of the atom. Now, roughly, so this guy here, so Louis de Broglie, he was a French physicist, and he was so about roughly in about 1923. 1923. He stated that electrons, like light, have the properties of waves as well as particles. So what they found was that if you take light, for example, so light can behave, depending on the experiment that you run, it can behave as a particle, which is known as a photon, or it can exhibit the properties of a wave, which has a particular wavelength. So a way to kind of think about that is there's this what's known as the photoelectric effect. So if you take, so let's say metal, and then if you bombard that metal with light, with these particles of light, which are known as photons, what will happen is this metal here will give off, or it'll kick off an electron. It'll knock off, if the particles, and remember, these photons of light, they're like, the way to think about it is they're particles that contain a very specific amount of energy, of light energy. And when they, for example, when they strike a piece of metal, that energy is absorbed by the electrons in the metal, in the surface of the metal. And if the energy is just right, what will happen is it'll knock off an electron. And this is what's known as called the photoelectric effect. Now, in this case, what's happening is light is behaving like a particle. So it's like you literally have this particle that's physically impacting the atoms, which can be thought of as particles in the metal, and then knocking off this other particle, which is known as the electron. So this was like experiments that were done, and these are properties that were being observed. And the same thing happens as well if you take light, for example, as we've seen, if you pass, so this is light, you pass it through a prism, it gives you a spectra, like we saw. So in this case, what's happening is light is actually acting like a wave. So what de Broglie proposed back in 1923 when he was doing his thesis was that, well, maybe electrons, so instead of thinking about electrons as these particles, maybe we can think about them as waves. And this particular observation or this proposal that de Broglie put forward was actually proven as well. So what they found is they did in this double slit experiment. So imagine you have a background like this. So this is a detector. And here you have, like, let's say, like you set up this like piece of apparatus that has two slits in it. And then imagine then you take, let's say, just a source that can emit electrons. So imagine this is just going to emit electrons and fire them at this particular plate that has these two slits in it. Now, what would be expected would be that you would have, let's say, just impacts here and here. You know, if the electrons, for example, are behaving like a particle. Now, what was actually found was that when they carried out this experiment, you got this kind of pattern. So instead of just having two lines here and here, what was happening was you were getting kind of lines here and here and here at different kind of intensities. So what that proposes is that when the electrons are coming to here, they were kind of, imagine they were acting like a wave. So you'll have these waves moving out like this, and you'll also have the same thing happening here. You have like these waves, and then what happens is, like, where these waves come into contact, they hit the detector here, and they give you this kind of like a wave. They give you a detection that indicates that the electrons are acting like a wave. Now, the weird thing as well about this is that this is the way that they behave when they're not being observed. When they are actually being observed, if you observe them, you carry out this same experiment and you observe the electrons, what happens is it's like they revert back to being particles. So this was kind of a strange, kind of effect that was happening. And then if you think about this, then if you apply this to the electrons, so like as in, like, you know, the electrons have this what's known as a wave particle duality. So wave particle duality. So that just means that the electrons can, depending on the experiment that you carry out, they can behave like a wave or they can behave like a particle. And that's kind of a hard one to kind of get into your head and try and kind of like intuit what that means and what that's like. So if we think about then, like if we think about like this whole effect and how when we apply this to the atom and then we apply it to the electrons in the atom. So imagine we have an atom like this, and as per the Bohr model, you know, we have these energy levels. N is equal to 1, N is equal to 2, etc. And this here is the nucleus. So in this case, and this is kind of like this is what was known as the planetary model. So imagine you have your electron that's here, and it's acting like a particle. And what's happening is when it's in this energy, in order for it to be in this energy level, it has to have a very discrete amount of energy. And what will happen is, when you go with the Bohr model, what happens is it just moves around like this in an orbit, just like the planets orbit the sun. And if we take these observations that were made by de Broglie, what happens is this kind of puts this whole model into question. Because basically what it's saying here is that the electron is actually, instead of behaving like a particle, it's actually behaving like a wave. So you can imagine, instead of it going around in these perfect circle, let's say these perfect orbits around the nucleus, what's actually happening is it's like the electron is kind of spreading out into this weird kind of wave, and it's behaving like a wave. So it's kind of spread out like this. And if you measure this, then what's happening is it's like this whole wave function collapses and it turns back into an electron. It has this particular, it turns back into an electron. And this is one of the, like, let's say, contributions that de Broglie made in relation to coming up with what we now have, which is a more accurate model, if you like, of the atomic structure of atoms and the arrangement of the electrons as well. So basically his input into it was that he stated that electrons, like light, they have properties of waves as well as particles. And as I was saying, this was confirmed by experiment 4 years later. And this discovery allied to the fact that the Bohr theory only worked well for simple atoms, and it led to the development of a more sophisticated theory of the atom. So if we remember, Bohr's theory works very well for simple atoms like hydrogen. It explains them very well, the spectra that you get, but it doesn't really explain more complicated atoms. And this kind of what this proposal that de Broglie made kind of indicates this. So you can see that it creates kind of problems with this simplistic planetary model of the atom. Then added to this, let's say, this kind of discovery by de Broglie, also as well we have this William Heisenberg, and basically what he said was that, and this is the Heisenberg uncertainty principle, it states that it is not possible to determine at the same time the exact position and velocity of an electron. So imagine you have, so you have your orbital like so, and you have your electron here. Now, what you could do in order to figure out the location of this electron, what you can do is you can shine light at it, and what will happen is you can then figure out from the light, from the way the light is reflected back, you can figure out the position of it. Now, the problem with that is that because these electrons are so small and they have such a small mass, that when these photons of light come along and they hit the electron, what happens is they can actually knock the electron off, like we've seen, like I mentioned in the previous experiment. So essentially it's kind of like, imagine if you had a basketball and you're trying to figure out the location of the basketball. And in order for you to figure out the location, you take these small tennis balls, and what you do is you fire the tennis balls at the basketball, and then they hit and they bounce and they land in a particular position. And then based on where you fire them and where they land, you can work out the position of the basketball. But what's going to happen is when you hit the basketball is going to actually change location. It's going to change location. So the same thing, this kind of principle then applies to electrons. So electrons are so small that when we try to measure them or observe them, the actual effect of measuring and observing the electrons has an effect on it. It's like it knocks them off course. So what happens then is that you can't figure out, you can't determine at the same time the position and the velocity. Because if you determine the position, what happens is you actually impact the velocity. If you try and figure out the velocity, you're actually impacting the position. So if you want to discover the velocity of something, so imagine you have an object. So in order to get imagine this object is passing in this direction, and you want to get the velocity of this object. Well, you have to take a measurement here and here. So you're going to get position, we say x, and then you're also going to get time. Okay, you have to get these two measurements in order to work out velocity. But the problem is with atoms, with electrons, when you carry out this first measurement, so for example, you fire your light and you get this first measurement, this first position, you can't get the second position, because essentially what you're doing is, because the electrons are so small, they have such small mass, when you measure it, you're actually knocking it off course, like so. So therefore, that's where this kind of Heisenberg uncertainty principle comes in, and it says that it's impossible, it's not possible to determine at the same time the exact position and velocity of an electron. So again, this kind of, blows holes in Bohr's model in relation to, thinking of the atom and thinking of the electrons like orbiting around the nucleus, just like planets orbit around the sun, in these perfectly observable and measurable orbits or levels. So there is considerable uncertainty with regards to the location of an electron in an atom at any given time. And Heisenberg, working in Germany after the First World War, realized that ordinary observation techniques could not be applied to electrons in atoms. So these ordinary observation techniques, and this is because they have very small masses, and so the disturbance caused by the measuring techniques must be taken into account. So in roughly 1927, so this is in roughly around 1927, Heisenberg stated his uncertainty principle, and this is the uncertainty principle. So the Heisenberg uncertainty states that it is not possible to determine at the same time the exact position and velocity of electrons. So this is kind of like where scientists were left with. What they were starting to notice was that, just using normal, what was called classical mechanics in physics, it didn't apply to when you got down to these really, really small masses and these really small particles, such as photons of light or such as electrons. There's this um, wave particle duality starts to kind of kick in, and things start to behave very weirdly when you get down into this quantum level. So then, because of this, because of all of this kind of uncertainty in relation to the location of the electron as it moves around the nucleus of the atom, with regards to its exact location of an electron in an atom at any particular time, it is more meaningful then to refer to the probability of finding the electron in a particular position within the atom. So instead of like kind of having it in your head that there's these exact locations where if you look here, this is where the atom's going to be, you have these exact orbitals, it's more useful to kind of think of it that there's different probabilities of you being able to find the electron in particular regions out around the nucleus because of all of these uncertainty principles and that I've talked about. It's actually, you can't really think about the atom like that. So the standard kind of planetary model of the atom doesn't really stack up well. So when you calculate this probability, use is made of the fact that the electron has a wave nature. So the probability is calculated using mathematical functions which are found by solving this thing, what's called the Schrödinger equation, and it was developed by this guy here, roughly back in, he's a German physicist, in 1926. So in 1926. So, and it's known as the Schrödinger equation, and it's attributed to this guy here that discovered it. So the way you can think about it then is, for an electron in an atom, there are a number of different mathematical functions that can be used, and if you use any one of these, what you can do is you can actually create like a boundary, and within that boundary you can have a high probability of finding an electron, and this region is called an atomic orbital. So that's kind of like what I want to talk about here. So this idea of what are known as atomic orbitals. And a way to kind of think about an atomic orbital is a region in space where around, for example, the nucleus of an atom, where the probability of finding an electron is relatively high. So again, instead of having like this kind of a model, like a planetary model, for example, something like so instead of having this kind of planetary model where you have the nucleus in the middle, you have the electrons like this, and they're orbiting around, they're moving around like this. So instead of thinking about it like that, the way the electron actually arranges itself, so instead of it acting like a discrete particle that just orbits around this nucleus, the way to kind of think about it is that the electrons kind of, they spread out, if you like, into this thing that's called an orbital. So we have this idea of what's known as an atomic orbital. So atomic orbital. And there's a couple of different, so if you think about, you have the energy levels. So you have this first energy level, n is equal to 1. So an electron that's in this first energy level, okay, it's kind of spread out like this. It's kind of like a sphere. Okay, it's spread out in a location like this. And this is what's known as an orbital, an atomic orbital. So a way of kind of thinking about it is, instead of the electron, instead of it going around in a discrete package, so the electron could be, so this is like a 3D sphere, so the electron, it could be anywhere within this region. It could be the way to kind of think about it is, it's actually like spread out and it's all over and it's here. And then if you come along and you make your observation and you put your light onto it, what will happen is this function, or this way that the electron is spread out, will all collapse, and then you'll just have this distinct region. The electron will be here, like so. So that's the way to kind of think about it. So you have these different, what are known as atomic orbitals. And these atomic orbitals, using the Schrodinger's equations, so he has an equation, they're quite involved and quite complicated. What happens is scientists are able to using, like, they can go and they can carry out experiments and measure, for example, the location of the electron. And what they find is when they actually carry out experiments and find the location of the electron, what happens is the electron is in different places every time they measure. So for example, you might run, for example, 20 tests, and in those 20 tests, it might be here one time, it might be here the other time, the electron, it might be here, it might be here the next time, it's here, it's here, it's here. And what happens is you keep building up this kind of like a picture, and what you find is that when you look for the electron, okay, it's normally it's in all of these different locations, but it's never here, for example. So the first electron that's in the first energy level, the one that's closest to the nucleus, the first two, for example, they'll always be contained within this sphere type of a shape. Okay, so they're all within here, and never outside here. So a way to kind of think about it then is it's like these two electrons, they kind of exist as this cloud, if you like, that kind of spreads around the nucleus in this particular shape. And when you look inside this cloud, when you specifically measure it, you'll find that it'll be, every time you measure it, it'll be somewhere different, but always within this shape, or within this sphere, or within this what's known as an atomic orbital. So then when you start to look at these orbitals, then what you find is that you have, so if we have a look at this table here, so you can see here, so we have like the energy levels here. So remember, a way to kind of, when we kind of looked at these, you have these, so you have these discrete energy levels. So imagine these are your energy levels, so the nucleus is down here, and depending on the type of atom that you have and the number of electrons they have, the electrons will hang out in these energy levels. So n is equal to 1, n is equal to 2, n is equal to 3, and n is equal to 4. So depending on the type of atom you have, the electrons will be kind of arranged, let's say, within these energy levels. And a way to kind of think about it is when an electron is in this n is equal to 1 energy level, it has a very specific amount of energy associated with it. Now, what we find is that what happens is there's actually these orbitals then, instead of the electrons like going around in these perfect orbitals, they exist as these kind of clouds, if you like, that are in this particular shape at each of the different energy levels. So in the first energy level, n is equal to 1, you have just this, the two electrons that exist or can exist there, they will kind of exist in this spherical type of a shape. Okay, so this is what's known as an s orbital. So this is what's known as an s atomic orbital. So you have, in the first energy level, you have one s orbital. So, and that in this orbital, you can have two electrons can actually fit in here. So a way to kind of think about it is you can have two electrons in here like so. And they will exist in this kind of a cloud shape, spread out around the nucleus of the atom. And then when you measure them, there'll be discrete particles that will exist somewhere within this shape outside the nucleus. Then as you go out, then what happens is, so if we take the second energy level, so two of the electrons exist. So two of them, if you like, So two of these electrons will exist again in the same type of this kind of a shape, in a spherical type shape, which is what's known as an s orbital. And then also as well, remember you can have, so this shows how many, so the first energy level can hold 2 electrons, the second energy level can hold 8. So 2 of them will be contained in a shape like this around the nucleus, and then the rest of them, so that leaves you with 6, you're going to have what are called, these are called p orbitals. So these are just different types of shapes that when the electrons are within this high energy level, they exist in this kind of a shape here. So each of these p orbitals, so you have p orbitals that are like this. So you have one, imagine you have a 3D, you have 3D axis. So you have an x-axis. So what will happen is you will get these kind of 2 lobes like this. And within each of these lobes, like you can have 1 electron. So it could be anywhere within, the electron could be anywhere within this lobe in here, like so. And the other one then will be somewhere like this as well. And this is the way they're arranged. So you'll actually have, you can have 3 p orbitals. They're arranged like this. So one will be along the x-axis like so, the other one will be along the y-axis, and then the other one will be along the like the z-axis, if you like. This is one that kind of goes into and out of the page. So the second energy level, or this is a little bit more further out from the nucleus of the atom. So when you think about the 8 electrons that exist, let's say, out within this space, up to 8 electrons can exist out in this space, and 2 of them will exist in this kind of a shape, and the rest of them will exist in these kind of a shape. So you have 2 of them will be in a shape like this along an x-axis, 2 of them will be in a shape like this along a y-axis, and 2 of them will be like this in a shape along the z-axis, which kind of goes back and out into the screen. So that's kind of like the way that these 8 electrons in the second energy level are arranged. So, and this is kind of like just what it looks like here. So the second energy level, you have, so this 2 here, so see the way they have it written as 2s, that just means 2 represents the energy level that it's at, and the s, the small s, represents the fact that it's an s orbital. So, and then you have these 3 p orbitals like so. So again, the 2 represents that it's in the second energy level, and the p represents that they're orbitals that are shaped like this. And then you have these 3, you have an xp orbital, this x, y, and z orbitals. So what we find is that so what happens is these p orbitals, the electrons that are configured like this in this kind of a shape, they're all, so the electrons, if you're to measure their energy, for example, they're all going to be equal. But what happens is that the electrons that are in this kind of arrangement are higher energy than the electrons that are in this kind of arrangement here. And then their orientation, so these 3 p orbitals are orientated at right angles to each other. So they kind of, imagine these, if you overlap these 3, they'll all be at right angles to each other. And then if you go out even further, then you go up further into the third energy level. So we see we can have up to 18 electrons in the third energy level. So it just gets a little bit more complicated. So again, in the third energy level, you're going to have an s orbital. You're going to have 3 of these p orbitals. And then you're also going to have 5 what are called d orbitals, and they're a different kind of a shape as well. So these the d orbitals can kind of arrange themselves like this. They're in this kind of a arrangement. So you have these d orbitals. This is a way to kind of think about it, is this is the way the electrons kind of arrange themselves into these kind of a shapes. Let's say, you know, the further, like when you get up into these higher energy levels. So then if you think about then the energy levels then, so the 3 p orbitals that are in the third energy level, they're equal in energy. The 3s orbital, so the s orbital, So you have one of these guys as well in this third energy level. It's arranged in this shape, and then it's of lower energy than the 3p orbitals. And then the 3d orbitals then are of higher energy then as well. So they're kind of above these then. And then it even gets more complicated then as you move up and up and up through the energy levels. So a way then to kind of think about it is, so instead of thinking about the electrons as these like particles that are moving around a perfect orbital within the outside the nucleus of the atom, it's more accurate to think of them as arranged in a what's known as an atomic orbital. So, and these atomic orbitals, they have a particular shape, and they're a region in space where there's a probability of finding an electron, where the probability of finding the electron is relatively high. So that's just a quick introduction then into what are known as atomic orbitals, and again, it's just a quick introduction into you know, Heisenberg's uncertainty principle and Schrodinger's his mathematics that was used to create functions, wave functions that could come up then with these predict or model these particular types of arrangements or shapes of the orbitals that are present. So the way to kind of think about it then is like a take-home way is that the way the electrons are, how the electrons hang out in the space outside of the nucleus of the atom is not as straightforward as just like simple, electrons orbiting in these perfect orbits. They actually arrange themselves in these kind of shapes, if you like, which are known as atomic orbitals. And these shapes, the way to think about them is they're regions in space where there's a high probability of finding particular electrons. So that's just an introduction, and we will kind of get into this in a little bit more detail as well. But it's just a quick introduction into this idea. So thank you for listening.